start off by looking at something we've already done, and then we're going to add something which is new, which is going to be, unfortunately, unpleasant. And this says this: if I know that, well, I guess we haven't done this, is if I know that the log of something equals the log of something, then those two things have to be equal. It's kind of like if I know that a to the x is equal to a to the y, then if the bases are the same, that means that the exponents have to be equal. This is far more important because it gives us a way of solving log equation or solving equations. It says if I have the log of a quantity, I have the log to the same base of the that quantity, then the two numbers, or two things, or the two arguments have to be the same. That also then says if these two things are the same, then I could take the log of both sides and they're still the same. It all hinges on stuff that we've done before. If I know that these two things are the same, if I square both sides, are they not still the same? Because I did the same thing to both sides. If I know that these two things are the same, if I square root both sides, are they still the same? Yeah. Now, all it's saying is, if two things are the same, if I take the log of both sides, they're still the same. And if I take the log of both sides and they're equal, then the two things on the inside have to be the same. Because otherwise it wouldn't make any sense. So if I were to look at this equation right here, in the past we would, and in fact we just did one over there, where we had to try to make the bases to be the same. I can't make 12 to be base 5, as much as I would try. So that says if I have these two things being the same, if I were to take the log, something which is on my calculator, log base 10, of both sides, that still is the same. What it enables me to do, using the properties of logarithms, is to bring the exponent down in front. The log of 5 and the log of 12 are just numbers. And that's maybe something that you want to think about as you're working problems. You could just change this into a number and then have them be numbers, and it wouldn't be as much of an issue. So I'll show you what I mean by that. Then I need to solve for x, so I divide both sides by log 5. This is then the log of 12 divided by the log of 5. This is an exact answer. Once I do the calculation, this is an approximate answer. Now, what I'm saying is that what you can do, if you don't like manipulating these symbols, and which is what they are, if I had 5 to the x equals 12, those two things are equal, but I can't make the bases to be the same. So I'm going to take the log of both sides. The log of 5 to the x equals the log of 12. One thing for sure that I know, or maybe don't know, as the case may be, but that you now need to know, is that the log of 12 is a number. So if I take the log of 12, it comes out to be 1.079181246, approximated to about 3 or 4 decimal places, and I could rewrite this equation as the log of 5 to the x equals 1.079. Now the problem's not so scary. Use the properties of exponents to bring the x down, so that I have the log of 5 is equal to 1.079. Now the log of 5 is just a number as well. So if I take the log of 5, it's 0.698970043. 0.699 would be okay. Now they're just numbers. So now what's x? X is 1.079 divided by 0.699. And I'm going to end up in the range of pretty much the same thing. I'm going to be off because I'm rounding 1.079 divided by 0.699. Ooh, that's interesting.
Yesterday we just did the log 5 divided by log 12.
That's the change of base formula.
Oh, I see. Okay, so that would be it.
Yeah. So this would be 1.544. Now, I got that number because I rounded. They did this number, and notice we're almost virtually the same. And a lot of it is because I've taken it out to 3 to 4 decimal places. Depends upon how you want to approach this thing. It's not going to be necessarily much fun.